Greetings of the day to all. My name is Angela OCHUGBOJU, a Ph.D. student from the NTSA group under the supervision of Professor Dr. Raf Andrejak. Have you ever wondered why the clapping of hands and a large audience suddenly becomes unified within the shortest possible time? This phenomenon is called synchronization. Synchronization, simply put, is the adjustment of readings of particles, or one could say objects, due to their interaction. Synchronization phenomena are a fundamental and universal concept observed in nature and in human life. We can find other few natural examples such as fireflies lighting up in synchrony, the synchronous chirping of cricket, the synchronous firing of neurons in the brain to power distribution networks in man-made systems. However, one common thing between these examples are the objects are not isolated. They respond based on similar objects in the environment. For example, a person hears the sound of clap his or her neighbor makes, or a firefly is being influenced by the light emission of a whole population. There are two basic types of synchronization: global synchronization and partial synchronization. Partial synchronization has attracted growing interest of researchers in recent times. Partial synchronization corresponds to the regime where one group of population moves in synchrony and the others are desynchronized. This coexistence of synchronization and desynchronization is also called chimera in the physics and applied mathematics communities. Interestingly, simple mathematical models demonstrate this surprising degree of synchronization, providing fundamental insight into many real-world scenarios. For instance, synchronization and desynchronization of the brain's neurons are essential for the brain to function well. In our research, we use mathematical models to understand how a large group of particles which interact behave and studying the different patterns they make based on their interaction. We want to determine if these patterns can remain in a specific state during time. We are studying coupled oscillators as particles that show partial synchronization even though they are all identical. We are currently working on a new reliable detection technique to classify the different outcomes. Surprisingly, we see that the different outcomes coexist for some parameter settings over a given time. To the best of our knowledge, no one has ever used these classification techniques in detecting and classifying partial synchronization. The model that we use is quite simple, but it serves our general purpose of classifying partial synchronization. We will apply our classification technique to networks made of different networks and more complex topologies. Thank you.